So my name's Alex. I'm a software engineer at Cockroach Labs. Before I joined Cockroach, I spent a couple of years on the core Kubernetes team at Google. So it's really cool to see these technologies come together so well and be able to talk about them in tandem. This is going to be a casual talk. Interrupt with questions anytime you want to. Raise your hand, just speak up, whatever. We're going to talk a bit about a number of things related to Cockroach and Kubernetes just a few minutes before we get into the demo. But yeah. Who here has been to a Cockroach meetup before? Most of you? And who here has used Kubernetes before? Used. Who has used? All right, got a couple? Cool. So we're going to briefly, just really quickly, world's fastest what is CockroachDB run through before we talk about how it normally gets deployed, and then that provides some context for how it gets deployed inside of Kubernetes. Then we'll do a really quick intro to Kubernetes for those of you who haven't used it, just so that we're all on a similar page, and then we'll get to the actual tutorial. So CockroachDB is a distributed SQL database. It tries to get rid of the limitations that you have to pick from when you're picking between a traditional SQL database and a NoSQL database. So traditional SQL databases can't scale up, or can't scale out, and are typically limited in availability to as good as a single machine can give you. But they give you lots of great guarantees that your data is consistent, that your writes won't clobber each other, your transactions are isolated. NoSQL, on the other hand, was built to kind of have the opposite trade-offs. So NoSQL scales out incredibly well, gives you great availability, can spread across data centers and the like. With Cockroach, we're trying to combine the two to get the best of both worlds, so that it's a distributed system that gives you high availability, it can scale out, but we still provide SQL and the semantics that implies. And Cockroach is a distributed SQL database that has a very cloud-native architecture. When you think of a cloud-native application, it's kind of a buzzword, but it typically means that an application can scale out, it can handle failures and recover from them automatically without needing any kind of operator help, and it can run on any hardware in a bunch of different environments. And those things all describe Cockroach. And those are the kinds of applications that are really meant to be run in Kubernetes, the ones that can scale out, handle failures here and then without any sort of effect on users. And so we're a distributed SQL database, and you can talk to any node in the cluster to get a consistent view of your data, to write your data, which works great when you're putting Cockroach behind a load balancer. So because you can talk to any node, you don't have to care about which packets your requests, or which node your requests are going to. Unlike if you're doing a master or secondary deployments, where you really have to make sure all your requests are going to the correct node. Here you can just stick a load balancer in front of it, talk to anything, which works great. Yeah? Hello? Yeah? Can you hear this now? All right. That is really loud. All right. So, yeah. So it's this thing that we call multi-active availability. It doesn't matter what you talk to. They're all identical. And it's really easy to deploy Cockroach, which also lets it fit well into cloud-native architectures. You can put it on any machines anywhere you want and manage it with ease. And the way that you typically deploy it is about as simple as it gets. So Cockroach is a single binary. It's statically compiled, and you don't have to have anything else running to make Cockroach work. No external dependencies. You don't need a naming service, a membership service. You don't need a distributed file system or anything. All you need is a machine to run it on, a disk to store your data on, and an IP address for nodes to talk to each other with. And once you get it all running, each node is symmetric. So killing node A would do the same thing as killing node B, would do the same thing as killing node C. So there's no real sense of one node being more important than others, being the master at any given point in time. And as you add nodes or remove nodes or add data or remove data, everything just gets rebalanced around the cluster automatically, so that you don't have to worry about anything as an operator. You don't have to worry about rebalancing data, changing hashing schemes or anything like that. And this makes it really easy to run Cockroach anywhere. So any cloud you want, we test it across all the big ones, put it in a VM, put it in a container, run it on the host. Run it in some weird emulated Linux thing if you're Joyent, but but you can run it anywhere. And it also works really well in orchestration tools like Kubernetes, Docker Swarm, as we're going to see today. So it's super easy to put anywhere and shouldn't take much effort to deploy no matter where you want to run it. And so that's where we get to Kubernetes. Kubernetes Probably means different things to different people at this point. It has so many features built in, it tries to do so many things, but at its core, its goal is just to be a system for managing distributed applications easier and more effective. So it provides dozens and dozens of features to this end that make it so that your distributed applications run better and are easier for you to manage with less operator effort. And CockroachDB is no exception. If you put it into Kubernetes, it will automate a lot of management things for you. And Kubernetes, of course, goes to a lot of effort to abstract away cloud provider specific things. So if you're running it on Amazon, you get a similar experience to running it on Google or on Azure. So it starts making you think less and less about the particular hardware you're running it on. And Kubernetes has a bunch of terminology that I'm going to be using quite a bit today. So just to make sure I'm not speaking over anyone, a container, when I say container, I just mean like Docker container. It's an isolated environment for processes to run in. It'll make it so things on the machine can't interfere with you, you can't interfere with them, and vice versa. A pod is this Kubernetes concept of tightly coupling containers together to run them on the same machine. We're not going to really use pods for anything much today, so you can kind of just think of a pod as a container for our purposes. When I say pod, you can just think I'm saying container, and it'll mean basically the same thing. A volume is this really cool thing where you can mount a different file system into your container so that you're not writing into the container's file system, which is typically a bad idea. And you can write it exactly where you would if you were running your process on the bare metal itself. Service is basically a way of grouping things together into a single network identity. So if I have a bunch of Cockroach pods running in a cluster, and I want to load balance all my requests to them without talking to individual Cockroach nodes, you put a service in front of them, talk to the service, and all your requests will be load balanced amongst the individual pods. And this controller is just a really core architectural concept in Kubernetes. There are these background processes that manage everything going on in the cluster. So you would have a controller if you want to ensure that there are a certain number of replicas of something running. So it's a replication controller or a deployment. You have a controller if you want to do auto-scaling based on some certain metrics. You have a controller to manage disks being mounted into the right place. Everything is done by controllers. And we're going to use a controller called a stateful set today. If you have spent a lot of time around people in the container community or the orchestration community, you've probably heard on many occasions that running a database on Kubernetes is a bad idea, or that running a database in a container is a bad idea. Some of these complaints were very valid a couple years ago, but have become outdated. Some of these arguments are based on assuming you're doing things the wrong way. If you do things the right way, and you're running on a recent version of Kubernetes, you can actually get a lot of safety, a lot of reliability running a database on Kubernetes. So one of these complaints, very valid but now out of date, is that when Kubernetes was first released a couple years ago, all of its controllers, none of its controllers handled persistent state. You couldn't have volumes attached to your pods in any reliable way. If a pod died and moved to another node, your data was gone. It was completely impossible to run a stateful application on Kubernetes at that point. But over the years, new controllers have been built that make this more feasible. Also, people in the early days of Docker tried running databases in Docker directly without any kind of orchestration framework. This often led to file system issues because they would try to store the data inside the container's file system. And containers in Docker are typically using less mature file systems that are not meant to handle high write throughput. It could lead to crashes, data loss, etc. If you're mounting a volume into your container, you get the same reliable file system that you would be using if you were outside of a container. So running a database in Docker is fine as long as you're not using the internal file system. And it really doesn't have to be that scary to run a database in Kubernetes. The multi-active availability model that I alluded to earlier makes it easy such that you don't have to think about individual Cockroach endpoints. You just talk to a service, and no matter where Kubernetes has put these things, no matter what's died in the meantime, no matter how many replicas you've added, everything just kind of works. Your applications don't have to care about it. And Kubernetes does really make it easier to manage applications. So you get a lot of benefits if you put Cockroach in Kubernetes along the lines of monitoring, health checking, doing upgrades, accessing your logs, all sorts of things, handling hardware failures. Cockroach recovers well from failures, but Kubernetes also recovers well from failures and will ensure that your application gets back up and running faster so that things will heal much more quickly. There are a couple differences though. If you're running a stateful application in Kubernetes compared to a normal one, if you're running like a web service, you'll probably put your pods, you'll create your pods via a deployment or a replication controller. We're going to use what's called a stateful set, which is this new controller in Kubernetes as of a couple versions ago, previously called a pet set, that treats pods as individual entities that have a stable identity and a stable disk. So that basically means their DNS name is not going to change across restarts, so they can consistently be talked to and talk to each other. And their disk is going to follow them as the pod gets killed and rescheduled across the cluster. So this is really important for making sure that we're not constantly losing our data and that the nodes can talk to each other even across restarts. And we're going to use persistent volumes, which is just a data volume that you can mount into your pod, and that will not go away if your pod gets moved to another machine. It can still keep using that same volume. So these are typically remotely mounted disks, like an EBS on Amazon or a persistent disk on Google Cloud. And so at this point, let's get into it. We're going to stand up a cluster locally on Kubernetes, and we're going to do a bunch of operational tasks with it. We'll take a little bit of a look at how this is being done, and hopefully get a feel for what it would be like to actually manage a cluster on Kubernetes. So if you do not yet have Minikube installed and want to follow along, now's your last chance. And if you want to, sorry?
So back to the slide with the Wi-Fi cluster.
Yeah, I think it's hashtag save the internet.
Sorry?
Hashtag save the internet.
Okay.
Yeah. They have great ambitions here. Cool. And so the commands I'm going to be using are available here at bit.ly/crdbk8s. So if you want to follow along without having to feverishly copy everything I type, I would recommend opening that up so you can copy and paste stuff. All right, so at this point, we're going to start up Minikube. So just to make sure you're running a reasonably recent version, you can run Minikube version. Hopefully you have 0.19 something at the very least. It'll probably work with older versions, but if you have 0.19, I'm pretty confident everything will go the same way. You can then run Minikube start to create your cluster if you haven't already. This will get you a local Kubernetes cluster running in a VM on your laptop. And it might take a minute or so, but once it's up, it's doing all this work to create the VM itself, to create all the Kubernetes infrastructure, the API server, the schedulers, the kubelets for the nodes. This will come up in a few seconds. And once it's up, we're going to do one final version check. We'll run kubectl version, which will double check your client's version as well as the servers. And hopefully there will be approximately 1.6 for Kubernetes. So at this point, we've got version major 1, minor 6 for both the client and the server. So hopefully you see something along those lines. And kubectl is just the Kubernetes command line client. It has 500,000 commands at this point, many of which are very useful, but take a while to find since there are so many. At this point, we're going to create the CockroachDB cluster. And we're going to use the kubectl create command that will go to this URL, download the YAML file that's at it, and create all the resources that are in it. And pretty much everything in Kubernetes gets defined via these YAML files. So we can take a look at it here. But we define a handful of objects in this YAML file, a couple of services, those networking concepts, and then the stateful set itself, which is going to run the pods. So here we've got this service called CockroachDB-public. That is the DNS name that anyone in the cluster that wants to talk to CockroachDB should use. So if you're running an application, you want to connect to the database, you can connect to this CockroachDB public endpoint to do so. And this is just defined as a service that matches all pods with the label app equals CockroachDB. So these labels are a dynamic grouping mechanism in Kubernetes that will match all of our CockroachDB pods. And we're going to hook the service up on ports 26257, which is CockroachDB's SQL and gRPC port, and on port 8080, which is CockroachDB exposes for an admin UI and some debug endpoints. So we're going to create that service. If we scroll down in this file, see what else is going on, there's a second service here. This service is only used internally by the stateful set, so no client is going to connect to this service. But it's part of what allows the stateful set to give each CockroachDB pod its own network identity. So we can skip down from there a little bit. We define a pod disruption budget, which isn't critical to running this, but it tells Kubernetes not to take down too many of the pods at a time during maintenance events. So if people are decommissioning nodes, Kubernetes won't go faster it won't go so fast that it takes down too many of your Cockroach pods at once. And here is the thing that's really doing all the work. So we've got kind equals stateful set, and we're calling it CockroachDB. So this stateful set has 3 replicas of the CockroachDB Docker image. And I'm going to skip over some detail in here. And it's going to run this Docker image CockroachDB/cockroach. So some of the detail that I skipped over is mostly around the initialization process of Cockroach, making sure that the pods join each other in the correct way. I'm happy to talk about that later. Do you have a question?
Yeah, sorry. Kind of reply, but you said that Kubernetes won't go so fast that it will make it unavailable because there's been availability, and I think I saw it scroll by to 67%. But in practice, if you have a large cluster, that thing's going to happen, right?
Yeah, it is possible, yeah.
Can you repeat the question, Alex?
Yeah, the question was, in a large cluster, is 67% enough to guarantee that things will be totally available? And it's not enough to guarantee that. If you have a really large cluster, 67% might not be enough.
So does this thing use persistent volumes?
Yes. So
eventually it will come.
Yeah. So we're mounting this volume. We're calling it datadir. We're mounting it at this path within the container. And that volume is being defined down at the very bottom of the file. So I just skipped to the bottom of the file. We have this volume claim template. And we're asking it to create a volume of storage class anything. So Kubernetes has this way of dynamically provisioning persistent volumes as you ask for them. So when each pod comes up, a controller within Kubernetes is going to see that it's asking for a dynamically provisioned volume and create a volume using whatever the cloud's default volume provisioning mechanism is. So it'll be a EBS or the like if you're running in a cloud. In Minikube, it's going to use just a memory-backed volume because it's just running in a VM. Are there any questions on this YAML file? I know there's a lot in it. I can go into more detail if someone has specific things they want to know. All right, so at this point, if you run kubectl git pods, you should have a few CockroachDB pods running. They've probably been running for a few minutes at this point, since they only really take 10 seconds to spin up each or so. But you've got these 3 pods running. Hopefully they've joined a cluster together. If you want to try verifying that, you can check out the logs for one of them. So we're going to check out the logs for the first pod and see if we can find its initialization methods down here. So yeah, we've got this CockroachDB node started at this time using the 1.0 build, and it's listening, at this admin UI address, this SQL address, and it initialized a new cluster. That's what it says it did. If you, do the same thing for one of the other pods, you'll hopefully see that it joined a cluster rather than initialized a cluster. So here's the second pod's logs. It's got node ID 2 allocated to it, and its status is that it initialized a new node, but it joined the existing cluster created by the first node. So that's what some of the logic in the YAML file is doing, making sure that the first node that comes up will create a new cluster, but all others will join into that first node's cluster. And at this point, I'm going to copy a command from the gist here, because it's a long one. We're going to open up an interactive shell inside the cluster. So we're going to use the kubectl run command. So that's going to create a new pod in the cluster. We're going to call it CockroachDB. It's just going to be the name of the pod. We're going to open an interactive terminal to that pod from our command line, which is a cool thing Kubernetes offers. We're going to use the same CockroachDB Docker image. We're going to remove it and not restart it once it closes. And we're going to run this SQL command connecting to the CockroachDB public DNS name that I mentioned earlier. So this is just a pod running in the cluster. We're not SSHing into one of the running pods. We're creating a new pod, and it connected to the existing CockroachDB cluster. So you can do anything that you would want to do with a SQL shell in here, and create databases, read tables, see what system tables we've got, all sorts, whatever you want to do with a SQL shell, you can do in here. If you're done messing around, you can press Control-D to send it into the file and get out of there. But that's just showing that you can get a separate pod running in the cluster, talking to CockroachDB. You can just talk to that load balance endpoint, and it'll be fine. What we're going to do now is run a load generator just to ensure that there's some steady load going on in the cluster to make things a little more interesting. So we're again going to use that kubectl run command here. We're going to call the pod loadgen, use a special image that we have that we publish called loadgen-kv. It creates a SQL table and then starts writing into that SQL table at a rate that we specify of about 100 writes per second. So we're not sending it that much load, just enough to give it something to do. And again, we're connecting to that CockroachDB-public DNS name. So at this point, if you want, you can see that the load generator pod is running. Because kubectl run turns things into deployments, it gets this weird string of numbers and letters at the end of it. But let's check out the admin UI. So Kubernetes lets you forward ports from your local machine into pods in the cluster. So we're going to forward our local port 8080 to the port 8080 in the CockroachDB 0 pod. So this will open up a direct connection from your laptop into the running CockroachDB process. And if you go to localhost :8080 in a web browser, you should be able to see the CockroachDB admin UI. So you'll see it's getting about 100 queries per second. It's got 3 nodes listed as members in the cluster. You can get information about things like the write latency, how many nodes are running in the cluster, details of how data is being replicated around the cluster, things like available disk capacity, all kinds of useful monitoring stuff if you want to see the health of your cluster. And once you've got that, let's try scaling up. So that port forward command is going to keep running unless you stick it in the background explicitly. So I'm going to use a separate tab. And we can scale what we're running. So using just the kubectl scale command, we're able to add as many replicas as we want. So we're going to go from 3 to 5. So I should say that it was scaled. And it's going to start adding those new pods immediately. So previously we had 0, 1, and 2. 3 is now initializing itself. And at this point, they're probably all there. So yeah, now we have 0 through 4 all in the running state. And if you flip back to the UI, you should now see the total nodes listed over there on the right. It says there's 5. Or if we go to the graph of node membership, you should see that we were at 3 for a while, and then just a second ago, we bumped up to 5. So now we've got more nodes. And so we've created a cluster, we're sending it some traffic. What happens if you kill things? Because things are going to fail from time to time. Machines will fail. Processes might crash for whatever reason. So if you want to simulate something failing, you can just delete one of the pods. So if you want to delete a pod, just enter some pod's name there. And kubectl delete, I'm missing the word pod in there. So delete pod and then the name of the pod. And so we deleted the CockroachDB 3 pod. If you look really quickly, you'll see that it got deleted, and Kubernetes is so fast, it's already recreating it. So we're not simulating a very long-term outage here. If you wanted to do that, a good way to do it would be to scale down. So like remove, say, the last node, scale down from 5 to 4 nodes. The 4 nodes that are left will say, hey, like the fifth one went away, what's wrong? I think it's dead. And after a few minutes, they would start to rebalance data appropriately amongst themselves. But in this case, a node was only down for a few seconds, so nothing too interesting is likely to have happened. We kept serving traffic. The admin UI didn't even notice that a node was gone because the thing was so fast. So Kubernetes recovers very quickly when things go away. Any questions to this point? Anything you want to ask about? No? Well, at this point, we can try doing a rolling upgrade. So say we started this cluster with version 1.0 of Cockroach. At this point, we've published 2 patch releases since then, 1.0.1 and as of yesterday, 1.0.2. So you might want to upgrade to one of those new versions, take advantage of the few bug fixes that got put in. So this is where the fact that stateful sets are still in beta kind of shines through. So stateful sets are not considered a completely finished feature in Kubernetes. They're still being very heavily worked on. Beta in Kubernetes basically means we think this is good, we're going to support it, but there might be things missing. We might change a couple pieces of the API perhaps. And what it means in this case is that they don't have a really good automated upgrade process yet. So rather than being able to just say kubectl upgrade to this version like you might be able to do with a deployment, we have to do something a little more manual. So if you run that kubectl edit command that I just typed in, so kubectl edit stateful set CockroachDB, you should see a terminal or a text editor open up. Search the resulting file for image : and all that's happening here is that when you run the edit command, kubectl will go download the existing state of the resource, display it here, and let you live edit it. So anything you change in this file will be saved and shipped back up to the API, to the Kubernetes API as a change to that resource. So for this point, we just add a .1 to the end here, and then save the file. We will have shipped up a new version of this file to the Kubernetes API server, and it'll have a new version. So you can check this. If we want to describe the stateful set, which will just print out its contents, and we can grep it for image here just to make the thing the output a little shorter. You'll see that other than the init container, which hasn't changed, the actual image that we're using here has changed to v1.0.1. So we're now running, or we've now configured a new version for the stateful set. What hasn't changed, though, is any of the pods. So we've changed the stateful set, but all the pods are still running, and they couldn't possibly have updated to a new Docker version, a new Docker image, without being restarted. That wouldn't make much sense. So you see they haven't moved. Nothing has been done. If you run that same describe command on one of the pods, you'll see they're still actually running v1.0. So Kubernetes hasn't gone and changed anything for the running pods. What it will do, though, is any new pods that it spins up will use that new version. So if you want to speed this along, you can go ahead and manually delete, manually kill all the existing processes, and Kubernetes will recreate them with the correct version that you want. So if you want to try this out, you can go delete pod cockroachdb-0. It deletes the pod. Kubernetes will very quickly automatically recreate it. It's taken a few seconds more this time. How about that? But when it comes back up, it's running the new version. So if you run that same describe command again, now it's on 1.0.1. So if you want to upgrade your stateful set, it's somewhat manual, but you can still do it by just changing your stateful set and going through and deleting all your pods one by one. So I've got a command in here if you want to do it. It's just the world's laziest upgrade command. It's just a little bash loop here that'll iterate over all your replicas, delete your pod, and then sleep for a few seconds. So I wouldn't recommend doing this in production. You might want to do it a little more slowly, maybe inspect things between steps. But this is basically what it's going to be doing in the next version of Kubernetes anyways. A PR to implement automatic upgrades for stateful sets was just merged within the last couple weeks. So it will be in the next version, which might be released in a few months. I'm not sure where they are in the release cycle. So this will go through and delete all your pods. Your UI might have stopped working because we killed the first pod. So you can just restart that port forward command and it should start working again. Right, and you can see, the number of live nodes has dipped a couple times as part of this upgrade. The SQL queries should still be getting served. At some point, the load generator pod might have to reopen a connection because the connection it had to one of the pods gets terminated whenever the pod goes down. So it's had to shuffle its connections around a little bit, and as a result, wasn't able to send quite as much traffic a couple times. You've got a couple little blips here where the load generator had to connect to a new pod, and that slowed it down a little bit. But the load generator will, it is just a program to reconnect. The Golang database SQL package will do this for you. It'll just reconnect as necessary. And now we've got this this fun warning popping up in the UI that you're running multiple versions in the cluster. It is part of a normal rolling upgrade process, but in case you forget to upgrade your last couple nodes, this will be a friendly reminder to you next time you open the UI that you did not finish doing your upgrade. So at this point, we've got one pod left. Does anyone have any questions yet? Has anyone run into any issues along the way? Something break? Yeah.
If your upgrade changes the behavior of the app, you cannot do this, right?
So it depends on the app, yeah. So Cockroach, we're very careful that doing an upgrade between versions won't break things. Like they can interact or interoperate just fine. So you could run version 1.0 with 1.0.2 permanently and it'd be fine. Once 1.1 comes out, it'll be the same story. You can run 1.0 with 1.1 side by side. So we'll make sure that that works. But you're right, that with some apps, this could be dangerous. Some apps don't play nicely with different versions.
So what is the purpose of the min available 67% again?
So 67% is not the best number, as Tamir pointed out. But if you're doing advanced things with your Kubernetes cluster where you're decommissioning nodes or like marking them one by one for node upgrades, Kubernetes will reschedule some of your pods. Like it'll have to move them around. If you do this, I don't have a good example of when it would be taking down a lot of pods at once, but Kubernetes will at times take down pods and have to move them elsewhere. And this just ensures...
Does that can also be applied to their rolling update solution?
The rolling update will probably be much like this, where it takes one down, brings one back up. The purpose of the disruption budget is to make sure that a minimum percentage of your pods don't get disrupted at a time. But 67% will not be perfect for larger clusters, as Tamir mentioned. So at this point, all of our pods are upgraded. Were there any other questions about this? Yeah.
Your buffer cache, do you guys do anything to save the state of the buffer cache? Or what would be the cockroach equivalent of the buffer cache between restarts?
As far as I know, we're losing the cache. Yeah. Because, yep. I mean, it's wiping away the entire container that was running. So.
I was wondering if there's anything like PG hyphen or something like that where like it saves the actual buffer page or the actual Postgres pages in default to the backend as fast as it can on process restart.
No, so I mean, yeah, that's not coming to mind. You want to pop something? Sorry, yeah. So the question was, is the Cockroach process doing anything to save the buffer cache across restarts? The state of the buffer cache, yeah. It is not, as far as I'm aware. Yeah.
What sorts of changes would you need to make if you wanted to run Cockroach across multiple Kubernetes clusters?
So the question was, what kind of changes do you want to make, or would you have to make to run Cockroach across multiple Kubernetes clusters? The trickiest thing there is going to be the networking. So Cockroach requires every instance to be able to talk to every other instance, which if your Kubernetes clusters are on the same network, will be easy. If your Kubernetes clusters are not on the same network, it could be very hard. And Kubernetes clusters are often networked in very different ways, depending on where they're run, with different overlay networks or other magic. So it works fine. Like we have set up clusters like this. We've done demos like this. But you have to make sure that all the pods can talk to each other individually. So the networking is the biggest thing you have to look at.
It's not just through a service endpoint, it's each individual node needs to it.
Yeah. So that's what the stateful set is doing for us here, actually. It's giving each pod its own DNS name, and so they can talk to each other using those names individually. So pod 1 can talk to pod 2 at a given name, knowing that it'll be there, even if it's been moved across nodes multiple times. So you can do it across multiple clusters, but we don't have a ready-made config for you because it depends on your networking setup. Anything else? So at this point, we don't have anything else we really need to do. Is there something else you guys want to do with this cluster? Otherwise, we can just tear it down, move on with our lives. You can delete things the same way that you create them. So just using the delete command. So we'll delete the deployment first, but so this will just take down the load generator. After we run this, the load generator will be gone. It's terminating, and it's gone. So at this point, the load generator is gone. And to delete everything else that we created, you can rerun the inverse of the create-f command. So just delete -f with the same URL. That'll tear down everything in your cluster. You have a question? Okay. It'll tear down everything in your cluster. Might take a few seconds to delete the pods because it's letting them gracefully terminate. Make sure that they've passed off any state that they needed to pass off before they died. And once that's done, so your port forwarding will stop working. And at some point soon, the stateful set should be gone. Did you have a, yeah?
So at what point in time, how would you monitor for capacity planning to figure out, like, hey, I need to go and add additional nodes? What's kind of like the rough rule of thumb or metric or ratio that you use for figuring out, like, hey, I need more nodes because I've got pressure in this particular?
Yeah, I mean, the two places you're going to hit, so the question was what metric are you going to want to look at to decide when you need to scale up to more nodes? The two main things you're going to want to look at are disk usage. Obviously, if you're going to run out of disk capacity, you need more, or CPU. So we're more likely to hit CPU issues before anything else.
Not RAM.
Not RAM, actually, yeah. So partially because it's written in Go, there's some GC pressure at times.
Right.
So you're more likely to need to add more CPU than to need to add more memory for most workloads. So you'd add monitoring of the CPU usage and then the disk usage. So we expose dozens and dozens of different metrics on a Prometheus endpoint, so you can easily plug us in with Prometheus. We actually have annotations already in the YAML file. If you have Prometheus running in your cluster, it'll just detect it and start collecting. And you could use that to do monitoring on things like CPU thresholds. At this point, everything should be gone from your cluster. You don't have those pods anymore. We don't have any services that had been there that I don't think I showed you earlier. But there's no CockroachDB services left behind. What is left behind that might not be obvious is the disks. So these are the persistent volumes that were created. So I did kubectl get PV. You could also do get PVC, and it's basically the same for our purposes. PV is short for persistent volume. So these are the volumes that were automatically created for the pods by the Kubernetes dynamic volume provisioner. So all these volumes are still around. So you can see they have 1 gigabyte capacity each. And they are status bound, so they are bound to these pods that we had been using. Kubernetes is very cautious to not delete your data, which, is kind of the obvious thing that you want it to do. So just because we deleted the pods and the stateful set doesn't mean the data is gone. If we were to recreate the stateful set, they would rebind to these same data volumes and pick up where they left off. So your cluster would not lose data. It would just restart with all the data that it had before. So I'm not going to do that now because it takes a few seconds, but if you were to just rerun that same kubectl create command, your data would all be right there. If you want to get rid of everything, there's a command in there at the end of the file. It'll delete all the persistent volume claims using a label selector. So every persistent volume claim with the label app equals CockroachDB will be deleted by this command. And then all your volumes will be gone. So don't do that unless you don't care about your data anymore. But I don't care about that data. So that's what we've got for the demo.
In the setup, is there a way to persist the logs, or is Prometheus answer that?
So by default, it depends on how you installed Kubernetes. So Kubernetes will, in most cases, have some sort of log shipper pre-built in. So if you use like the common scripts for spinning it up on Azure, or on AWS or GCE, there's often an instance of FluentD running on every machine, which is grabbing the standard out and standard error from every container running on every machine and shipping that up somewhere. So if you're running on Google Cloud, it'll be shipped up to Google Cloud Logging or whatnot. If you're running on one of the other clouds, it might be sent to an instance of Elasticsearch running in the cluster. But yes, the logs will typically be saved by Kubernetes without you doing anything for it. The data, however, will not. If you delete the PVs, the data is gone. So CockroachDB is a very scalable database, as you are aware at this point. You can run it easily in Kubernetes, as well as other environments, obviously. And it works really well in these orchestration tools. Kubernetes is doing a lot for you to make it easy to check out the logs, to keep it up and running when things fail.